let's get started. It was an interesting, it was a really interesting preparation. Gavin, just a couple questions for you. You did a lot of work as well. I think the blog that was related to this was about what, 14 pages long?
Yeah, it was long.
It was very long. There was a lot in this, and just let me get started by saying that there are very few ground rules. We just ask that you mute yourself if you're available to talk. I really encourage everybody to turn on their video if they can. It's better to see people, particularly on the heels of COVID. It's nice to see faces. The recording is ongoing. I think it's running right now. Is that right, Gavin?
Yep.
Perfect. It's an open mic. It's a discussion. It's not meant to be a lecture. What we do is we research the topics, then we select information from the topic. We drive very deep into that. We tend not to go as broad as we do deep on a topic, and there's a reason for that, because this is a very complex environment, and the IPCC's AR6 report was no exception to that rule. So I encourage everyone to ask questions. Gavin will keep an eye on the questions as they come in, and there is no bad time to ask a question. Ask away. There are 29 slides. We're going to go through them fairly quickly. We have I think a phenomenal handout for this one, which actually has the relative GWP impact for refrigerants. We'll be sharing that sometime before the end of the day tomorrow. So let's get started and move through. All right, so today we're talking about IPCC's impact on refrigerant management. And we're going to pick a very specific, narrow focus today. We're not going to get really broad. This is a 3,900-page document. Anybody here has read it. You're aware of the fact that in addition to the chapters and the tables and the reference material, there are over 6,000 people that contributed to this. This was a real big release for IPCC, and it was much larger than previous releases. So it's taken months for us to go through and really understand its impact, and so we're going to drill into the specifics related to refrigerant today. All right, so we're going to start with some really high-level things. But going back just one second, my name is Ted Atwood. I've been doing this for 28 years in one form or another, but always focused on the idea, the concept, the goal of reducing refrigerant emissions. That's the plan. We find that we can get there. Anybody can get there by knowing what their emissions are and understanding what the options are available to them. So that is the ultimate goal. Although TrackRef is the extension of many years of learning from a large team of people that are devoted to this, and we call ourselves refrigerant geeks. So to get started, IPCC is the Intergovernmental Panel on Climate Change. It was a very straightforward group focused on advancing knowledge related to climate change and the impacts that people have made on the planet. It's begun in 1990. It was begun a few years earlier, 1987, but the first IPCC assessment report was released in 1990 and talked about the challenges of global warming, the consequences, and the suggestion that international cooperation was needed in order to advance the knowledge and the solutions required related to the impact. There have been, as of today, 6 synthesis reports. The first 5 are fully released. We tend to release one, or there tends to be one released. I make it sound like I was part of it. I did do reviews, but not part of it. And anybody can do that. Happy to teach you, show you, share with you ways to participate in the review process. But the first 5 have been released. The last one was 2014. Before that, it was 2007, 2001, and then 1995. So we're on about a 7-year release right now. The 2014 version was released in 2014, but it wasn't finally published until 2015. And the same is true for AR6. So that was released at the end of last year, but we're in the final phases of edits right now. And it is not fully published on the website just yet, but the tables are all there and the review period is ended. So we can consider AR6 in the books. So I want to go back to AR4 for a minute. This was really a substantial part of the evolution of the assessment reports. It was published in 2007. As this slide states, it was the most detailed, thorough examination of climate change that had ever been undertaken. There were 6,000 peer-reviewed studies that were part of the outcome from this. And AR4 was the most commonly referred to reference guide for refrigerants that are presently used today. We're going to talk about those in detail in a minute. But AR4 was really important globally and also in the refrigerant community. All right, my screen is frozen. There we go. AR5 was the 5th in the series of reports published by IPCC, and it was published in 2014. And as the slide talks about, really the most significant thing to come out of AR5 in the refrigerant world specifically was the awareness that a 20-year GWP factor was more valuable or referentially valuable to the refrigerant community, because most refrigerants don't have an atmospheric life that reaches 100 years. R12 does, for instance, but there are very few that last 100 years. And so the quick summary on AR5 related to refrigerants are that the AR5, the published AR5 report with tables and reference suggested that there was a better evaluation of refrigerants' impact on the environment or the climate if we used a 20-year life cycle instead of a 100-year life cycle. That was really significant. We're going to go through and we're going to get all the way across all the 20 and 100-year numbers and what they mean. There are 3 working groups that are part of this IPCC process. Working group 1 deals with the physical science based on climate change, and that's really the one we're talking about today. But for reference, working group 2 are climate change impacts, adaptations, vulnerability, risk. This is where they talk about what's happening. And working group 3 is mitigation of climate change. And this is where they talk about alternatives primarily. We're not going to talk about numbers 2 and 3, although happy to have a discussion related to those if anybody has any questions. This is a 3,969 page document. If you're in the refrigerant world, focus on chapters 6 and 7, but primarily focus on chapter 7. Chapter 7 is where all the action takes place. Chapter 7 starts on page 1842. Oh, sorry, 1618. But our charts that are really valuable to refrigerant people are on page 1842 and focus on box 7.1 if you're looking for reference material. Box 7.1 will tell you about the resource related information that was used in the refrigerant modeling, and also the general modeling for the accountability. And I'll go through that in a second. But these are the key and new elements in this document that are here on the screen related to AR6 versus AR5. And we're going to go back and forth between AR4, AR5, and AR6 throughout the discussion. Amazing stuff happened in the modeling, and the technology is better. International treaties are better. For those of us who are near my age, when we started this journey back in the 90s, climate modeling was limited to where treaty and boundary lines were drawn for Eastern Bloc countries, primarily before that. This really wasn't a possible, none of this was possible pre-1990s. But what we found is this energy budget. We talked a lot more discussion in here around radiative forcing. I don't want to get too complicated, but what is so fascinating is they're able to now model refrigerant emissions by doing air sampling. And to give you an idea how complex this is, we're talking parts per billion measurements here. It's not a lot. It seems, and it's a very low amount. And that's why in the refrigerant spectrum, this is very important. Essentially, it's like a droplet of water out of a tiny eyedropper in about 13 gallons of water. All right, so that's about what they're picking out of the air when they're doing this evaluation. I was fortunate enough to see some of this firsthand, these results in the 90s when we were doing some work with some large steel plants, and they were evaluating air quality in the region around the steel plants, and they were pulling out things like krypton, argon, and they were separating that from air. And these were very inefficient, large Russian air separation facilities. It was really impressive to see it. But now they've taken that modeling from this very physical environment, and they're able to create projections out of it, and it's amazing. And having read through this report, now I've gone through it, I would say 1.2 times, one full time through all 3,900 pages. And then I've gone back through and read chapters 6 and 7. I guarantee you I'll be referring back to this document numerous times just to continue to understand everything that's in there. But there were some major improvements in AR6 over AR5's science and sensitivity and modeling, and all of those things come through, and they provide us with a real deep, granular awareness about our carbon budgeting. And at a very simple level, this is basically what the carbon budgeting is made up of, comprised from. And I've got a few slides to share with you on that. Any questions so far, Gavin?
Nope.
Okay, good. So, and there are several influences here on the energy budget. Of course, radiative forcing, climate feedback, and sensitivity. We're going to talk about how those things are impacted by refrigerants in a minute. I have two slides away, and I have some really interesting graphics that were part of IPCC's report. But the modeling was greatly improved. And this table 7.9 gave significantly more insights, which created better confidence about the numbers. And it also, once you can improve on these numbers, it does improve the modeling, and it gives us a much better idea of things like cloud formation impact on global climate. Let's call it radiative impact. But I'll share that slide with you next. But all of this improvement, and I guarantee there'll be improvements in the next one, because most of these improvements evolved up through 2019, because we really started to see the data in 2020. And that's when we had to or they had to stop the modeling process so that we could get that information, or that information could be gotten into the hands of people, lay people like myself and science people, for analysis. And they had two amazing charts here. And I say amazing because these were really valuable. This chart represents the global mean energy budget. And as you can see up here, and I think I can turn this into a pointer. Hold on, laser pointer, there we go. As you can see from up here, we have this incoming and we'll talk about this a little bit more deeply over the next 3 slides, but we have this incoming energy, this outgoing energy, what gets trapped both under the clouds and when there's no clouds. Okay, so I want you to notice the numbers. Okay, these are important because we're going to refer back to them periodically, but how less heat makes its way out. And without going back too deeply into this, because I don't like to get super granular and kind of overly geek out, but what I would tell you is as more liquid from ice is in the atmosphere or in the environment or here on Earth, what ends up happening is it creates more clouds. More clouds create an additional layer of complexity in how we measure and report on these emission numbers. So basically, every drop of water is increasing the amount of thermal retention that we store here on Earth. And they did such an amazing job in AR6 that I think we'll spend the next 5 years while AR7 is being prepared, because it's already started, just understanding the impacts here. And these impacts will also then become part of the foundation for AR7. This is all additive, so it's all evolving. But basically, you get the idea. In an all-sky environment with clouds, we have less outgoing watts of energy. As energy comes back in, we have our surface area that's retaining more of this. Some of it's retained in the oceans. Some of it's, and as water is added to the oceans, it does give us more of a carbon sink to hold that. But this is now all modeled very well. And I'll show you what those 3 additional impacts are related to greenhouse gases in a minute. But I want to stop here and just mention that with no clouds, you notice that the numbers indicate a best magnitude of scale for release of let's say watts of energy. And our uncertainty numbers are published here. This is our range. Anything in parentheses is a 340 or 341, 265 to 270. So this is our range of numbers, and we have an average that they've published in here. And these are all 21st century numbers, so it's also important to note. But also another special mention on this is that the equilibrium with no clouds, let me get this straight because I made some notes. Let's see. Yeah, the equilibrium with no clouds represents a global mean flux as determined solely by removing the clouds, but otherwise retaining the entire atmospheric structure. This enabled them to do better modeling and measure the effects of the clouds on Earth's energy budget, and corresponded to the way that the clear sky impacts were calculated. So again, this is in chapter 7. I found that these were very useful. There's a lot of reference data related to them, and I'm happy to share that afterwards. Now, basically what's happening is we're measuring watts of energy, and what you're seeing here, watts of energy are relative to what's received, not emitted. All right, so this was interesting because if you notice over on this side, we have ozone and they have the mean bar, but we have a reduction in ozone and we have an increase in the radiative impact, radiative forcing, radiative impact, similar. And this is measured between 1750 and 2019. Of course, they do a lot of analysis on ice samples to get this information. And anyways, you get an idea of where those radiative impacts are. Refrigerants are right in here. Now, this is actually calculated in the atmosphere. These measurements are taken in the atmosphere. This is it's very important to be aware of that, because we struggle as a marketplace, as a community, to calculate emissions. Although the EPA has signaled and indicated that 100% of all refrigerants produced are emitted. Only a small fraction of refrigerants produced, and it's less than 1%, much less. It's less than 0.5%, are actually destroyed. You'd be surprised to find out that the refrigerant destruction marketplace in the United States is very limited. It's limited globally. Very, very little refrigerant emission, controlled refrigerant emission technology available out there today. But keep in mind, this is power received, not emitted. And what refrigerants are doing is they're not adding more power to the atmosphere. They're capping what power received from the sun can actually leave. I hope that makes sense. All right, we're more than halfway. Any questions so far? Chase, Roya? There we go.
Yeah.
All right, good. Now, GWP, basic stuff. Anybody who's already done this before, my apologies, but for anybody who's new to the topic, just wanted to make sure you were familiar. GWP, global warming potential, and it was developed to allow for a comparison of global warming impacts on different gases. CO2 is a 1, everything else is not a 1. So CO2 is our benchmark gas. Refrigerants are referred to as high GWP gases because for a given amount of mass, they trap substantially more heat than CO2. We're going to go through some of those specific numbers. However, it's important to note that the atmospheric life ranges for these materials are limited to decades, maximum decades. I mean, R12, 100 years, I believe, but everything else less than 100 years. Except for a refrigerant that's not used often as a refrigerant, R14, which does have a life cycle, atmospheric life of, I think, 50,000 years. So that's not what I would refer to as an SLCF or an SLCP. SLCF is a short-lived climate force. These are gases and particles that affect the climate. They have lifetimes that in the newer generation, like 1, 2, 3, 4 YF, only last a couple of weeks after they're emitted to a couple of decades. Many of these are also listed as air pollutants. This is an important note because anybody who's been working with these materials for long periods of time know that if you have above a certain amount of materials, then you may also have the responsibility to report for other regulatory purposes. Paul, great question. Let's get to that in 1 second, but I appreciate you asking it. Paul's question is, why does 750 seem to me to be the magic GWP benchmark? Paul, I think it's kind of arbitrary based on all the research. These are just numbers that industry have accepted, but they're certainly not numbers that the scientific community's accepted. By the way, there are 3 factors that drive the refrigerant conversion factor. Number 1 is how much is in the atmosphere. I'll show you a great chart on that. Number 2 is how long do they last? So like what's the average life? See that in the next slide. And what's the strength of well, it should have been radiative force, but I'll share that. I'll fix the slide when I'm all done. My apologies. So does that make sense to everybody? Okay, now 1, 2, 3, and 4. I want to call your attention to the red line right here. This line is the left boundary of the lifetime. So this is the atmospheric life of refrigerants. And I picked out a few that I thought were important. R22 has an atmospheric life of 11.9 years. You'll see it rounded up to 12 in some cases, but this conversion factor came right from the IPCC's AR6, published report, chapter 7, page 1842. You'll notice that these other refrigerants down here, and I picked out a section that I thought was valuable, R123, which is an HCFC also, has an atmospheric life of 1.3 years. And I hope you guys can see these well enough, but R125, which is incredibly common, is 30 years. R134 is 10. And R134A is 14, but we tend to use 134A. So those are the two that I'm giving reference to there, the 125 and the 134A. Now, if we keep going to the left, we're going to get to this orange line. Now, this is very important. This is the global warming potential at 20 years. Now, let's see. I'm going to do something here. While we're talking, I'm going to launch a poll. You guys take the poll while we're talking. I'll keep talking. You take the poll. You stop me if you have any questions. And at the end of this, we're going to say it will include a survey. It's all anonymous, so it won't matter, but it's interesting to know what knowledge is out there related to refrigerants, because it helps us, refine and align with where we need to focus our energy in sharing insights. Now, here's the GWP, the 20-year GWP. The 20-year GWP, you will hear me refer to as the AR5 factor. The 20-year GWP for R22 is 5,690. The 100-year GWP based on AR5 is 1,960. I mean, based on AR6, my apologies, is 1,960. This is slightly higher than the 1,810 that's part of the AR4 values. These values all changed, as I mentioned before, based on those three things that I mentioned to you, including the radiative impact, how long it lasts, its life, atmospheric life, and also how much is in the atmosphere. The more in the atmosphere, the higher the number. So as we continue to measure the atmospheric impact, these numbers will continue to evolve. But notice that it's 5,690 when we calculate it across 20 years, but 1,960 when we spread it out over 100. And I'll show you what that chart looks like in a minute. But the reason this is so important is because once we take the atmospheric lifetime into consideration, as well as those other two, then what we find is that the impact from that is higher. Then I went ahead and I added two more lines in. So the GWP for the 100 year is here. And then the number 4 is something called the GTP, which this is the global temperature. Hold on, I don't know how to shut that off while we're doing this. There we go. The GTP. Does everybody here know what GTP stands for? Global temperature potential. So what you might find over time, and now the global temperature potential at 50 years is 785 for R22. All right, and it's 379 at 100. Now, I would not be surprised to see more use of the GTP factor in the future. But when I say the future, I'm talking 8 to 12 years away. Maybe it'll be fewer, but in my experience and everything that's happened with the AR4, AR5, and AR6 publications, it takes about 7 to 8 years for the data that gets published in the IPCC's report to become mainstream data. So now you were asking the question earlier, Paul, why does 750 seem to be the magic benchmark? Well, we're going to have to start asking ourselves, is that 750 the AR4 750, the AR5 750, or the AR6 750? And likely answer will be, we'll see more use of the AR5 factor. Already the IPCC, through the Paris Accord, have called for the use of AR5's values and factors in reporting global inventory emissions, US greenhouse gas emissions included. Now, that's a really heavy statement. Does anyone have any questions about that? All right. Now, why does that make sense? There are 4 charts here that help us understand what this looks like. as you can see, the refrigerant, like R32, and I picked one of 7 examples. I thought this one was the best one because it had the most conforming structure across the board. And temperature range up here, temperature ratio from pulse emissions, this is over time. Now, of course, R32's life is 5 years, 5.5 years. So we have a reduced impact on both temperature. We have a reduced impact on both temperature and global warming. So see, I am not hitting anything and it keeps making this change. So we have reduced impact over time. And this is exactly how it should behave since the molecule only lasts for 5 years. So we get to see how those years affect R32 or HFC 32. Now, why this is also important is that you'll notice it goes up slightly here, temperature ratio for step versus pulse emissions. It goes up slightly because there's an expectation in the modeling that R32 will continue to build in the atmosphere. And as I'm going to share with you in a minute, the R32 numbers, like all refrigerant numbers, are largely underreported on both the greenhouse gas inventory and on company balance sheets. Paul, great follow-up question. California and others have settled on a number required to regulate this at 750 based on AR4 because that was baked into Congress's AIM Act. However, what you'll find very soon is that all companies will be reporting on the AR5 factor. So regulations may be based on AR4, but reporting will be based on AR5. And I'll get to that as we get towards the end, because we have some advisory information that we were able to pull from EPA's comments. But does this make sense why refrigerants' 20-year life cycle matters more than its 100-year life cycle when calculating its GWP factor? I'll assume that's a resounding yes. Going to keep going. All right. The EPA greenhouse gas inventory report, if you read that, is about to go and shift from AR4-based 100-year values to AR5-based 20-year values, and that is going to take place in 2024. This is really important to understand, and I'm going to share some additional slides with you and give you some visibility into what the future looks like based on this shift. If you've gotten used to the factor of 1810, and you've gotten used to these AR4 factors, you're already using data that is 15 years old and is evolved. You're looking at AR4's published year was 2008-9. So those numbers were 13 years ago. Sorry, I thought it was 2007. It was published in 2007. Those are 15 years old. Very important to note that those numbers have evolved based on those 3 criteria that I've mentioned to you. But legislation and members of Congress and government tend to be at least 6 to 8 years behind in their data absorption capabilities. So everything that you're looking at will be reporting. We're going to make the adjustment to reporting. Those numbers will go up. But when you're writing regulations to guide manufacturers towards what's their allowable number, you're going to find that that number is based on the AR4 factors that were published in 2007. Now, if you're a manufacturer or you're out there and you're doing service and you're thinking to yourself, well, we're doing everything just right, why are shareholders mad? Why are activists and advocacy groups telling people that they need to do better? It's because the numbers have moved on, even though the manufacturing base has not. Now, this chart, these are the AR4 published values in white. These are the ones that we're all very familiar with. But these are the real GWP factors that we're going to see used by the federal government in their greenhouse gas inventory reporting and all governments around the world. So just keep in mind, We're going to have one set of tables to reflect on what we're allowed to use for manufacturing and application in the field. And we're going to have another set of values that we're using to report. So as I mentioned, AR4 published in 2007, but we did not start using AR4's values in greenhouse gas reporting until 2015. So it took 8 years. Now we're seeing that although the Paris Accord passed, I believe, 2015, and it did call for the use of AR5 factors in reporting, here we are in 2022, and we're seeing those numbers be used starting in 2024. So it's a 10-year gap from the time we got those numbers shared with us through IPCC to the point where we use them. That's a really big deal. Now, these are also the factors that you'll be reporting on when you're reporting. So if your shareholders are expecting you to meet regulatory requirements, you can be right on target with those, yet you can miss your GWP emission numbers, your drive to net zero, because you're about to double and triple the GWP impact from those refrigerants for reporting purposes. So the distance between you and net zero just got a little bit longer. And that's what you want to take away from this thinking process. Now, if you're wondering, does it matter at all? These are just a bunch of accounting numbers. Well, we reported about 4.8 billion pounds of leaked refrigerant during the 8 years that it took the US government specifically to adopt the IPCC's AR4 numbers. All right, so we leaked about 4.8 billion pounds, fairly sizable number. And I'm going to put that in perspective in a minute. And we'll share this chart, but does anyone have any questions about these numbers? And it should frighten you that using the 750 benchmark number that was shared earlier, that was mentioned earlier, none of the refrigerants other than R123, which is now an obsolete banned substance because it is an ozone depleting material, none of them meet the GWP threshold of 750. So I'm going to move on if I don't have any questions. Either that or everybody's just waiting until the end. All right, here we go. This is the 2020 published inventory emissions in the US for our greenhouse gas inventory. Now, if you'll notice, it reports a 3% F-gas as part of our overall greenhouse gas emissions numbers. Now, for those of you who've been part of these annual discussions that I host constantly, and I've been doing this now for 4 years, the US government was only reporting 1% of total greenhouse gas emissions as refrigerant emissions up through the end of 2019. So if you're wondering, how did we go from 1% to 3% in 1 year? Did we have like the greatest year of refrigerant emissions in history? The answer would be no. The answer is that the US greenhouse gas inventory emissions report is based on a lot of feedback and input from the marketplace. And we have been complaining about this since 2014. And the reason we're complaining isn't because we feel like these numbers mean anything to many people, but we're complaining because it takes the visibility away from the overall refrigerant emissions. And this number is actually underreported as well. This number is underreported by about 35 to 40%, because this only accounts for roughly 326 million pounds of refrigerant emissions. And the projected pounds on refrigerant emissions, if they are allowed to equal total production and imports, is closer to 600 million pounds. However, the EPA felt like that 600 million pound number was too large. And so they didn't want to disclose or report that number because it would have brought this 3% number up to 6%. Now remember, the EPA is collecting data through greenhouse gas inventory segment under the EPA's greenhouse gas reporting protocol responsibility. In the electric utility segment and in our segment here, this group, we would be reporting under subpart DD. The problem is only a select few companies are responsible for reporting there. That if you're on the toxic release inventory reporting radar and you have to report there, then you would report your emissions. But most companies don't report all of their emissions because they don't know them. So when we try to build our empirical values up from the bottom, we're missing over 300 million pounds of emissions. However, when we look at this from a macro perspective and we calculate emissions based on whatever is produced is vented, that number is 600 million pounds, which would double this value here. Now, adjusted emissions in the future using the AR5 20-year factor that I shared with you earlier will more than double our emissions here in the US without actually accounting for the missing refrigerants. So we're going to go from 350 million tons of carbon, roughly, to 700 million tons of CO2 equivalent when we make the accounting adjustment for the 20-year life cycle instead of the 100-year life cycle. Which, if you did the math, and I didn't bother to publish it here, would bring the total refrigerant emissions impact in the US on our entire greenhouse gas inventory to roughly 12% of emissions, which is a 12 times factor increase from what the federal government published in 2019. Happy to answer any questions anyone has. That's a lot of information right there. All right, how does 12% of overall emissions relate? Like what's the relatable impact? Well, EPA and global governments are going to continue to evolve their awareness on this topic, which better informs accountability, which has already yielded a 300% increase in the reported CO2 impact from refrigerants. And when we make this adjustment from AR4 to AR5, it's going to increase the number again. But as I mentioned to you before, the CO2 number stays the same. 1 will always remain 1. But what's going to happen here is we're going to go from 100 million tons of CO2 equivalent in 2019. So that's our 2019 number, as I mentioned, that's published in the US greenhouse gas inventory. We're going to go to more than 900 million tons of related CO2 with the same emissions level in 2024, just because of improved accounting and a shift to AR5. What that does is it makes refrigerant emissions a greater CO2 factor globally than all of the air traffic from all the airplanes and their CO2 emissions from fuel consumption. This is taken from a group called the ICCT, the International Council for Clean Transportation. This is their 2020, October 2020 published data, which reflects on the published 2020 data from EPA's US greenhouse gas inventory. And what I really wanted to share with everybody is when you really stop trying to adjust accounting practices and you stop messing with the information that the marketplace has access to, and you just account for the actual pounds and the transfers, refrigerant emissions outweigh air travel in CO2 impact. And when the AR5 numbers are used and the marketplace has to adjust to a reporting factor that's greater than the reporting factor than they're using today, and if you haven't planned for that or budgeted that, then you're going to be out of line or out of alignment with what shareholders and ESG Scope 1 emissions reporting is going to expect, because that's all driven by IPCC. All right, so what should you do? The plan. use AR4 presently, just like you're doing. The EPA is going to move to AR5 reporting in 2024. So you should start modeling your carbon budgets using AR4 and AR5 20 and 100-year factors so that you have an idea about what this change in emission factors will look like for you. And that's it. That's all we've got. We're taking a 1-month break. We'll be back on July 21st. We're going to talk about corporate governance for HVAC techs. It's really important. This is the bridge between owners, operators, and the service teams that do the work. Between now and then, 4th of July. So hope everybody has a very nice 4th of July. And I'll get together with Gavin and we'll get you a fantastic reference document for these AR4 and AR5 values with all the common refrigerant types on it. I think there's like 19 refrigerants. And we'll share that probably by the end of the day tomorrow. All right. Gavin, are there any questions?
Nope.
All right. I see that only a couple people took the survey. Everybody, I really encourage you to take the survey. We don't use it for marketing. We really use it to help refine the information that we publish here and the research that we do. We do a lot of research on these topics. I hope you guys all find it valuable. And if you don't come back. But if you do, please help us to keep improving this. We really take this seriously. So, Gavin, Roya, Chase, and you want to add anything?
It's a constantly moving target for everybody, right?
Yeah. But it's really important that you understand the difference between AR4 and AR5 and why that value is important and why that factor is going to be used by governments for accounting purposes, but it may not have any impact on regulations, which are very hard to change. So if the AR4 factor is built in, and that's the one you have to go with, you may be using that for your operation, but operations needs to know how to speak the language of investor information. And that's where that AR5 factor will come in. Paul, thanks for your comments. I really appreciate it. Everybody have a great day.
Thanks.